We have 3 plenary lectures for this morning. The first one is going to be given by Dr. Nicot. He is from the National Research Institute of Science and Technology in Grenoble, France. I thought I always pronounce it as Grenoble, and I was told it's supposed to be Grenoble. Anyway, he is the head of the geomechanics group in the institute. His research is in grading of materials with the interactions with the protective structures, such as debris. So let's welcome our speaker.
Thank you very much, Mr. Chairman, for this very kind introduction. Thank you to the organizer for giving me the opportunity of these plenary lectures. So, first of all, I would like to introduce my co-authors. First, Professor Félix Darve and Luc Sébille from Grenoble University, and also my 2 PhD students, Zhu and Yen. The presentation I will give is a part of their PhD work. So this morning I would like to go down to the microscale using DEM approach, and then to analyze, to investigate what we can observe on the macro scale and try to interpret these features by going down to what happens on the micro scale. So this is the content of my presentation. I would like to focus on 4 chains and grain loops and try to analyze the interplay between these two bodies. And I would like also to discuss failure and microstructural patterns. And then I will move to some concluding remarks for the future. So if I present very shortly some results coming from biaxial tests, you can observe some very classical, some very usual results. This is a biaxial test, a biaxial simulation run from DEM. You can observe the evolution of the deviatoric stress and also of the volumetric strain, considering different specimens, loose or dense. And you can observe that according to the initial world ratio, you have different evolution. You may have a peak and then of softening, or you can have monotonously increasing deviatoric stress. The problem I would like to investigate is the following one. I would like to understand why in some cases we can have this kind of peak and softening. What is the origin of the strength, of the mechanical strength in the specimen, and why this strength is limited, is bounded? And also I would like to make a parallel between the strength behavior and also the volumetric behavior. On the right, you can observe the evolution of the volumetric strain, and this evolution is not the same according to the initial void ratio. So I would like to investigate why we have this kind of features just by considering what happens on the micro scale. So if we go down to the macro scale, we can observe this kind of patterns. We have a set of grains, a set of contacting grains, and in yellow we have what we call a force chains. I think that most of you are quite familiar with this notion. Force chains is an assembly of grains, of contacting grains, transmitting high forces. This is a well-known notion introduced by Drescher, de Josselin de Jong, and of course by Rajai, mostly discussed by Rajai, and after by Tordesillas, Kreut, and so on. And this kind of force chains are surrounded by the gray particles. The gray particles are the so-called weak phases, and these phases, more or less, is built with cycles. You have grain cycles, grain loops, and I have a great interest on these loops because the stability of the force chains will be directed by these loops. And according to the number of grains you have in a loop, the stability, the stabilization of the fortunes will be not the same. Thus, I am going to investigate the behavior of this kind of loops according to the number of grains. My presentation will be limited in 2D conditions, just to try to propose a framework that could be extended afterwards in 3D. So basically, we have the following scheme. You have the granular material, and in dark blue you have the fortunes. In gray you have the weak phases, composed of loops. You have the different loops on the right with 3, 4, 5, or 6 grains. So I will denote these loops L3, L4, etc. And what we know is that the fortunes are responsible for the stress behavior, so are responsible for the mechanical strength of the material. And this is a well-known result. That means that as soon as we have fortune buckling, then we have a limitation in the strength of the material. But we would like to know why we have buckling in some cases and not in other cases. And the response could be on the right, could be in the context of the loops. Of course, the loops will stabilize the fortunes, but also the loops will govern the volumetric behavior of the specimen. This is why we can have a sort of parallel between both strength and volumetric behavior in a granular material. The results I am going to show you were obtained using DEM code, YAD code, developed in Grenoble. This is a very classical DEM model, close to the molecular dynamic. We have only 3 parameters defining the local behavior between 2 grains, introducing a normal stiffness, a tangential stiffness, and a friction angle between the grains. Grains are assumed to be spherical. This is the parameters used during the simulation. More or less, we have 10,000 grains. And I am going to consider 2 specimens just to analyze the influence of the initial porosity, a loose one and a dense one. So this is the result we have obtained. We have considered a biaxial test run from the two specimens, the dense one on the left and the loose one on the right. And on this slide, we are going to analyze the evolution of the different cycles. This is what we call omega. Omega I means the ratio of the different cycle, of the different loops. And we try to analyze how this ratio evolve over the loading path. What we can observe is that I have also represented in blue the evolution of, just above, I have represented the evolution of the stress, of the deviatoric stress, and of the volumetric strain. And you can observe that we can correlate the evolution of the different ratio with respect to both the deviatoric stress and the volumetric strain. Which is also interesting is to plot the number of buckling, of fortune buckling. This is above, this is the blue curve. What do we observe? We observe in red that the number of loop 3, that is to say the loops containing 3 grains, is decreasing up to a plateau. On the contrary, this is the purple curve. You see the purple curve is increasing. I can show you with my mouse. You have the curve increasing. This is the number of large loops. So starting from a dense specimen, the very dense clusters containing 3 grains are decreasing, and on the contrary, the number of loose patterns containing 6 or more grains is increasing, and the clusters, the loops containing 4 or 5 grains are more or less constant. More interesting is that you can observe that the buckling, the 4-chain buckling, increasing just a little before the stress peak. And also you can observe that the maximum slope in both the omega 3 and omega 6 coincide with the minimum of the volumetric strain. So that means that we have a close connection between the evolution of the microstructure on the mesoscale and the macroscopic behavior of the specimen described by both the deviatoric stress and the volumetric strain. We can also investigate a little bit more what happens by separating two families. We can consider We can consider the loops in connection with 4 chains and loops that are not in connection with 4 chains. And of course, what is very interesting for us, this is the loops in connection with 4 chains, because this is those loops that are going to play a role in the stabilization of the 4 chains. The loops we have in the gray part are not connected to 4 chains. So as a first step, as a first approximation, we can ignore the plays a role in the macroscopic behavior of the specimen. In what follows, I will focus mainly on the loops connected with 4 chains. Oh, okay. I will stay near the microphone. Sorry. So this is the result we obtain by distinguishing the 2 families of 4 chains. So on the left we have we have the loops in relation with 4 chains, and on the right we have the other 4 chains. What we obtain is that the behavior of the loops is absolutely not the same according to the families they belong to. If the loops belong to the left family, that is to say, if the loops are connected to the 4 chain, what we observe is that we have a stronger dilatancy within those loops. On the contrary, the dilatancy is smaller in the loops far from the 4 chains. So, as a result, we can conceive that the dilatancy near the 4 chains is much more important. What does it mean? If we have dilatancy in 4 chains in relation with in loops in relation with 4 chains, then we develop loosest structures, and those structures are less prone to stabilize the 4 chains. As a result, 4 chains may buckle. This is also what we can observe on this slide. I have plotted the evolution of the void ratio according to the different families we have. In the loops connected to the 4 chains, in the loops outside, far from the 4 chains, and everywhere in the medium. You can observe that the blue curve, that is to say, the curve indicating the most important dilatancy, is related to the loops closely attached to the 4 chains. And on the contrary, the red curve, indicating a less pronounced dilatancy, is related to the loops far from the 4 chains. So the loops in the surrounding of the 4 chains have the trend to dilate, and then they lose the capacity to stabilize the 4 chains along the loading path. What I would like also to show is the evolution of the different families of loops in the vicinity of the 4 chains. Considering that we have initially a dense specimen, we can conceive that the ratio of very dense loops containing 3 grains is important. What happens over the time? This is what we plot here. The different curves, red and blue curves, indicate the evolution of the different ratio of loops. The blue curve corresponds to the loops with 3 grains. The red curve corresponds to the loops with 6 grains. What we observe is the following. We observe that over the loading path, progressively, the ratio of loops containing 3 grains is decreasing, and on the contrary, the ratio of loops containing 6 grains is increasing. 0 means the time at which the fortune has appeared, and 1, it is the time at which the fortune has disappeared. So, as soon as we are approaching the end of the fortune, the ratio of loops containing 6 grains is increasing. So, it's an important result because that means that the stability or the instability, the buckling of fortunes, is intimately related to the nature of the loops surrounding the fortunes. The more you have very dense cycle, the more the fortunes are stable. Another point also corresponds to the nature of the stress tensor that we can analyze within the mesostructure. Mesostructure means loops with 3 grains or loops with 6 grains. And what we observe is that the loops with 6 grains is the most anisotropically stressed structure. This is what we can observe with the different curves by analyzing the deviatoric stress within the different cycles, the different loops. So, as a result, when you have 3 grains, the stress tensor is more or less spherical. I say more or less spherical. And when you increase the number of grains, then progressively you tend toward something more anisotropic. Anisotropic means that even though you have a very important axial force that applied to this structure, the lateral force will be smaller if you have an important number of grains. This is no longer true if you have something with a small number of grains, typically with 3 grains. If you applied a vertical stress, an axial stress, then the lateral stress you can observe with this structure will be more or less of the same magnitude of that you have in the axial direction. And these have very important consequences on the behavior of the specimen. You can observe on this slide the scheme we have in mind. This is a proposal, of course. This is what we are thinking. Imagine that initially you have a dense specimen. Dense specimen means that you have a great number of loops with 3 grains. So what happens? As soon as you apply an axial stress, then you can observe that the lateral force applied to the boundary walls is very important. But you have to adjust the motion, you have to adapt, to adjust the displacement of the wall just to fit the lateral pressure. As a result, what happens? If the lateral forces are very important, then you have to move outward the lateral world. And as a consequence, the specimen will dilate. If the specimen will dilate, what is the consequence? If the specimen dilates too much, then you will destroy the very dense structure with 3 grains, and on the contrary, you will create structures with 6 grains that are much more dilatable. So, as a result, if you have too much 6-grain structures, the fortune will buckle, and thanks to this buckling, you have a stress peak, you have a limitation in the strength of the material, and you can observe a softening regime. If I have a few minutes again, I would like to show you some results in relation with failure. This is some slide that I have already shown in the previous session of this conference. I have introduced the second order work. The second order work is a quantity that we can derive using the kinetic theorem energy. This is what I have written down on this slide using an Eulerian description and a Lagrangian description. In what follows, I will use a Lagrangian description. It's more comfortable because I can differentiate this equation very easily because the domain of integration are fixed. This is what I have done on this slide, and I obtain a relation giving the evolution of the second derivative of the kinetic energy, and we can show that this second derivative of the kinetic energy is finally the difference between two terms, an external second order work and an internal second order work. The failure for us means that we could have an increase in the kinetic energy, and this increase in the kinetic energy is due to the difference we can have between the internal and the external second order work. So this is why in the following I will focus on the internal second order work, assuming that the external second order work can be zero. So if we assume this, we can focus on the internal second order work, and going down to the microscale, we can also re-express the internal second order work using the classical variables we have when you consider a discrete material, that is to say, the relative motion between the relative velocities between the relative displacement between the grains and the contact forces. This is what we have. This is what we did, and then by doing so, we can derive this relation, in which we express the internal second order work with the branch vectors and the contact forces. The second term on the right-hand side, the equation can be omitted, and finally, we can focus on this term. This term is the local, is the micromechanical second order work. This is for us an important term because it makes it possible to characterize the stability of the material on the very local scale, just by making the scalar product between the incremental evolution of the contact force and the incremental branch vectors. Contact C minus means that the value of the second order work, this second order work, is negative. And in what follows, we are going to track where are the points, where are the contacts at which the local second order work, the micro second order work, is negative. So we consider exactly the same biaxial test shown previously, and using an initial dense specimen, you can conceive that we may have a localization, a strain localization near the peak or just after the peak. This is what we have obtained. You can observe on this slide a very nice localization, a very nice strain localization, and what we are going to plot is a distribution of the local second order work. On this slide, we are just before the peak. You can see that you observe a negative value of the second order work on the right, and this is the blue. This is the red, the blue point. You have the negative value of the second order work, more or less, almost in the same zone in which we have the strain localization. What happened a little bit further? We run the same analysis, but in the softening, after the softening regime, then you have a very nice shear band. And as you can see, you can observe that in the same zone you have a very nice localization of the contact where the second order work is negative. So the local second order work is clearly negative within the shear band, that is to say, where you have the failure zone of your specimen. We can correlate this analysis with some microstructural analyses in relation with the different loops we have, loops with 3 grains, loops with 6 grains. This is what we did, and you can observe that at the different stage of the loading, we have an evolution of the microstructures, and at the end, you can observe that within the shear band, then you have just a small number of loop 3, and on the contrary, we have a high concentration of loop 3 outside the shear band. So inside the shear band, you are very dilating, you destroy the dense structures, and on the contrary, you are promoting structures with a large number of grains, that is to say, structures prone to dilate. We have exactly the same result, not with 3 grains, but with 6 grains. And you can observe that you have a localization of the loop 3 within the shear band, where the concentration of this kind of loop is much higher. Just before closing my discussion, my presentation, I can show you an analysis to prove that the distribution of the different loops is absolutely not homogeneous within the medium. We can use a coefficient to characterize the heterogeneity of the distribution, and exactly at the localization point, that is to say, exactly at the stress peak, you can observe that you lose the homogeneity of both the distribution of L3 and L6. Starting from a very low value. A low value means that you are more or less, that you are mostly homogeneous. And when you increase close to 1, then you are becoming much more heterogeneous. This is what happens just after the peak. Okay, now I can conclude my presentation by coming back to the main result. So we are characterized the evolution of the mesostructure within the specimen by comparing the ratio of L3 and L6. We have correlated this evolution with the 4-chain buckling responsible of the mechanical strength of the medium. And we know that the transition from L3 and L6 determines the volume change in the specimen. This is an important point. And when strain localization occurs, we have observed the following shear band. We have a concentration of unstable contact within the shear band, and we have an increase in very dilatant, in a very loose loops, and on the contrary, a decrease in the very dense structures. So I take the opportunity to make an announcement for a conference that could be of interest for you. This is the next EMI conference that will be organized in France in 2016, so in 1 year. And this conference will be in particular in relation with discrete approach, discrete analysis. So if you need any further information, feel free to ask me for any details. Thank you again for your very kind attention.